In this lesson, we're going to go over volumes of solids of revolution again, using both the disk method and the washer method. But this time, we're going to be revolving around an axis other than the x-axis or the y-axis. So let's just jump right into an example. So we want to find the volume of the solid created when the region enclosed by this function and the line x equals 1 in the interval from y equals 1 to y equals 3 is rotated around x equals 1. So the first thing we're going to do is draw this out. So if I have this function here, it's going to look something like this. And it's also bounded by the line x equals 1, which is this line here. And then from 1 to 3. And the region that we're looking at here is this piece right here. And when we rotate it around x equals 1, it's going to look something like that. And notice that x equals 1 is parallel to the y-axis. So we're treating this the same way as we would if it was being rotated around the y-axis. So the circles that are going to be our cross sections are going to be going this way. Pardon my bad drawing. So we have the function is in terms of y, and that's also a good indicator that we're going to be doing this in terms of y. And we know that x equals 1 is parallel to the y-axis. So those cross sections that we're using are circles. So we know that the area of each of those circles is going to be pi r squared. Now the difference here from what we did last class was when we're finding the radius, remember that the radius is going to be either the top minus the bottom or the right minus the left, and it's in relation to the axis of rotation. So last time when we were revolving it around the x-axis or the y-axis, those functions are both 0. So either x equals 0 for our y-axis or y equals 0 for our x-axis. So we only really used the one function that we had because we are technically subtracting 0. But now we're actually going to be subtracting something else. So again, we're focusing on the blue piece, the piece that I kind of shaded in yellow here. So for this radius, the rightmost function is going to be the negative y squared plus 4y minus 2, and the leftmost function, is x equals 1. So to find the radius, it's going to be the right function, which is negative y squared plus 4y minus 2, minus the left function, which is 1. Okay, so just to kind of recap again, last time when we went over the x or y axis, we were really subtracting 0, but in theory, we were still subtracting the second function, it just was 0. So here our second function is 1, so we're subtracting 1. So I'm going to rewrite this radius to kind of clean it up a little bit. So I have negative y squared plus 4y minus 3. So now we're just going to do what we did last time, and we're going to say that the volume is going to be, we're going to pull out that pi since that's our constant. The integral is going to be going from 1 to 3 because that is 1 is our lowest y value and 3 is our highest y value. And then we have our radius, which is negative y squared plus 4y minus 3. And we have to square it because it's the area of a circle. And then the width of each of our circles is going to be dy because we have everything in terms of y. So we could either find the antiderivative or plug this in the calculator. And if we do that correctly, either way, we should get 16 pi over 15 as our volume. So let's look at another example. So find the volume of the solid created when the region enclosed by that function and the line y equals 4 is rotated around y equals 4. Okay, so again, let's sketch this out. So x squared plus 4x plus 4, for graphing purposes, if we can remember that that is actually x plus 2 squared. So this is just a parabola with the vertex moving left 2. So it's going to be, this is going to be, whoops, oh, that's not so good. Let's fix that. Whoa, something like that. Pretend that that's not a squiggly line. Okay, so there's my function. Then I have y equals 4. So that's going to be the line that's, whoops, pretend that that's straight. It's not, but pretend. Okay, so here. So we're looking at this piece. And we're rotating it around y equals 4. So we're going to have a rotation, up like this. So y equals 4 is parallel to the x-axis. So when we make our circles, they're going to be going this way. Okay, and again, we're focusing on this blue piece, or the piece that's colored in yellow here. We have our cross sections that are circles. So we're using area equals pi r squared. And then we have to figure out what our radius is. So remember, we want to be doing, in this case, since it's related to the x-axis, we want to be doing top function minus bottom function. So for focusing on the piece I colored in yellow, the top function would be 4 minus the bottom function, which is our x squared plus 4x plus 4. Okay, so we always want to do top function minus bottom function. So I'm just going to clean up this radius. I'm going to distribute in the negative. So I'm going to put this in order here, make this negative x squared minus 4x. And then this 4 and the negative 4 will cancel out. So my radius is just there. So I'm going to start setting up my integral. So I'm going to pull out that pi since it's my constant. I need to find my limits of integration. So that's going to be where I have points of intersection on the two functions. So what I'm going to do is just set the two functions equal to each other. So let's do x squared plus 4x plus 4. And we're going to set that equal to 4. So when I go to solve this, we'll get x squared plus 4x is equal to 0. I'll factor out an x. So now when I go to solve, I'm going to end up with x equals 0 and x equals negative 4. So right here, I'm just going to put a little dotted line here. That's negative 4 and that's 0. So my integral is going to be from negative 4 to 0. And then my radius is negative x squared minus 4x. And we have to square that. And then our width of each circle is going to be dx. So again, from here, we've been doing this for a while. We can find the antiderivative or plug it in the calculator. And if we do it correctly, we should end up with 512 over 15 pi. And there is our volume. Okay, so both this example and the previous example, we're using the disk method because we only had one function and the line of rotation, and it was flush against that line of rotation. So now let's look at a couple of examples that use the washer method. So determine the volume of the solid generated by the region bounded by y equals the square root of x, y equals x squared, and rotate it around the line x equals 2. So first thing we should do is do a quick little sketch of this. Again, sorry for my artwork. So y equals the square root of x is going to be like this. Y equals x squared is going to be like this. And the line x equals 2 is going to be like, let's say it's like right here. That's x equals 2. So we're trying to rotate around this. Now notice that the line of rotation is not touching our functions. There's a little gap between it. So we know that we're going to be using the washer method here. So this is very, very poor on my part. Let's see if I draw this like this and like this. Oops. Okay. So it's going to look something like that as the rotation. And then my, this is really terrible. My circles, whoa, are going to look like something like this. So this 3D shape is very bad, but it's going to, oh no. Okay. So let's just pretend that that looks semi-decent. So I'm just going to color this piece in yellow. So that's what we're focusing on. So we need to figure out where we're rotating this figure. So since we're rotating it around the line x equals 2, we know that x equals 2 is parallel to the y-axis. So that means that we need to be using functions that are in terms of y. So what we have to do is change our functions so that they are in terms of y instead of in terms of x. So we have the first function, which was y equals the square root of x. If we solve that for x, we end up with x equals y squared. And then we have our second function, y equals x squared. And if we solve that in terms of y, we get x is equal to the square root of y. So when we're finding our big R and our little r, because we're using it around something that's parallel to the y-axis, we're going to be doing right function minus left function. For our big R, we are going to be using the line of rotation as our farthest right function, and then our left function is going to be the farthest away from that line of rotation. So our line of rotation is at 2, that's our right function, minus our farthest left function, and then that is our square root of x, which we changed to be y squared. Our little r is again going to be right minus left, so our rightmost function is 2, which is our line of rotation, and then we're going to subtract the closer function as our left function, so that is x squared, but when we changed it in terms of y, we have the square root of y. So now we just write our integral. So I'm going to pull out that pi since it's my constant. Now to find my limits of integration, I need to find my points of intersection here. So I could take the two functions and set them equal to each other, and we'll get 0, 0, and 1, 1. So our limits of integration will be in terms of y here because we're dealing with everything that's in terms of y. So we're going to be going from 0, which is our lowest y, to 1, which is our highest y. And then we have big R squared minus little r squared. And the width of each of these circles is going to be dy. And then if we were to solve this, we would end up getting that v is equal to 31 over 30 pi. So we could plug in the big R and the little r in place of this and find it by hand. We could also figure it out in the calculator. But as long as we're identifying big R and little r, we can just use those instead. Okay, so let's look at the last problem here. So determine the volume of the solid generated by the region bounded by y equals x squared minus 2x, and rotated around the line y equals 4. So first thing that we'll do here is we'll do a, quick little sketch. So y equals x is going to be about here. X squared minus 2x is going to be something like this. It's going to be rotated around the line y equals 4. So we'll just put a little line here and call that y equals 4. When we go to rotate this, it's going to look really not like that at all, but something like that. And then our circles are going to go, something like that. And here's this really, terrible shape. Just pretend it looks good. So I'm going to highlight in yellow here. So what I colored in is what we're focusing on. So the line of rotation, which is y equals 4, that's parallel to the x-axis. So everything's going to be in terms of x that we're doing. So we need to identify our big R and our little r. So big R, because we're going in terms of x here, and we're going around an axis that's parallel to the x-axis, we're going to be using top minus bottom. So the top function in this case would be our line of rotation, which is 4, y equals 4. So my top function is going to be 4 minus my bottom function. And I want to get the bottom function that's farthest from the line of rotation. So that's going to be this x squared minus 2x. And then for my little r, again, top minus bottom. So my top function is going to be the line of rotation since it's above my shape. And then I'm going to subtract the bottom function. And in this case, the bottom function is going to be the closer function to the line of rotation, which is x. So now I'm going to set up my integral. So I'm going to have my v is equal to, I'm going to pull out the pi, since that's my constant. And because I'm rotating it around y equals 4, which is parallel to the x-axis, I have to use the x's for my limits of integration. So what I'm going to do here is just take the two functions, x and x squared minus 2x, set them equal to each other. So we're going to get x squared minus 3x equals 0, factor out the x, so you get x minus 3 equals 0. So we're going to end up with 0 and 3. So here's 0, and then here is 3. So we're going to go from 0 to 3. And then we have big R squared minus little r squared. And then the width of each of these circles is going to be dx. So then we just plug this in a calculator or find it by finding the antiderivative, and we end up with our volume of 153 over 5 pi.